What method did we just kind of go over? We just went over the capital P-value method. Your author says this is the method to use because it's what's done by most statisticians today. Now, we mentioned that there's other ways to try and figure out what the population proportion is. There's the traditional method. In the traditional method, I have a critical region. And I just basically reject if my test statistic is in it. Is in what? The critical region. So what was the critical region? Is this a one-tailed or a two-tailed example we just did? Two-tailed? All right. So then the critical region looks like this. There's two tails. I should go back and look what those z-values were. Here we go. The z-value was 0.98. That was my test statistic. So my z-value, my test statistic, was 0.98. Okay? The z-value for the critical region, that's called the critical value. So whatever this z-value is here, these are called critical values. This is the traditional method. And if you have an older stats book, this is all they're going to tell you. By the way, any guess what these critical values are? I'll give you a hint. Alpha was 0.05. So this was 0.025. And sure enough, this was z equals 1.96, and this one is z equals negative 1.96. How do I figure that out if I don't have it memorized by now? How do I figure that out if I don't have it memorized? I could do inverse norm of 0.025, and you know what it would spit out? This one, because that would give me this much area. It would give me negative 1.96. Okay. But anyways, what do? I look at my test statistic was 0.98. So where's that in the picture? Well, it's below this, right? It's right around here somewhere. Okay, so what do you think? Do we reject or fail to reject the null hypothesis? Fail to reject, right? We only reject if my test statistic is in the critical region. That's the traditional method. So you can either look at p-values and compare them to the significance level, but the traditional method is draw a picture. And I think both approaches are worthwhile. One last approach. Hey, if I give you alpha, you could construct a confidence interval, right? This was what we did in Chapter 7. Right? When alpha is 0.05, what kind of confidence interval are we constructing? 95% confidence interval. That's another way to go after what the population proportion is. I don't think I want to do that today because I'm focusing on Chapter 8. But I think on Tuesday, if you want, if you say, hey, give us an example of a confidence interval, I'll come right back here. Okay, we'll go back to the same problem. David? Yep. Well, we reject H naught if my test statistic is in the critical region. Where's the critical region? Well, the two tails. My test statistic was right here, 0.98. See that? That's not in the tails. so I didn't reject. Yeah, we fail to reject. That's right. You only reject if this thing is so far out there that it's in one of the critical regions, one of the tails. Okay? Scott? No. That wouldn't reject either. You only reject if you're way out here somewhere in the critical regions. If it was past it. That's right. Okay. Oh, yeah. The last thing to say about section 3. You know, in that problem, how did we get p hat? Well, I think what we did was 57 divided by 104. Remember that? That was my p hat, which was 0.54, something like that. Sometimes they just tell you p hat. They say 10% of the observed sports cars are red. Well, then you have the proportion, right? Sometimes they tell you the percentage of the sample. Sometimes you have to calculate it, right? If they said this statement, look at this one, it's a good example. 96 surveyed households have cable TV, and 54 do not. Oops, sorry about that. Actually, we did a little informal survey in here. Some of you were telling me you don't have cable, right? Well, if I wanted to know what's p hat, the proportion, does this make sense to you that this is how you get it? 96 divided by, well, you'd have to add those together, right? Because that'd be the total. N. Does that make sense to people? Yeah? Jim? Yeah, you should know all 3 methods. You should know p-value, you ought to know what traditional is, and you ought to know confidence intervals. That's chapter 7. Yeah. Scott?
So then with that first example, what would the 90% like the other percent parts not? Is that kind of
You could call it q hat, but I don't know. We don't usually use that. Sure. Craig? Yep, that was chapter 7. There's the traditional method where you're drawing this picture. And then the one I did before that was p-value, capital P, which we went over. Yep. Let's do an example. This example is from chapter 7, M&Ms. This was problem 25. Shelley, tell me what it was. What section? Or what page or something? 45, I'm sorry. Number 45 and 7-2. I decided to show you this because it uses StatDisk and because it's a way we can talk about all the things we've been learning. I kind of like this problem. Here. Page 343. Okay. And I don't know if some of you are going to be using StatDisk for the stats in your paper. I don't know. You're welcome to if you want. I mean, you could even write a paper that uses some of the data here if you wanted. But you don't have to. You could use your own data. Anyways. I punched up StatDisk. Here we go. Now, to use StatDisk, you know, for these problems that say use the Appendix B data sets, right? First of all, is everyone at the page? I don't want to go too fast. Let me pause for a second. If you ever are using StatDisk and you want to get any of the data that it says is in one of these data sets, there's a little icon up here. Oh, by the way, can you see this at all? Or is this too small? People in the back? Okay. Hang on. Okay. Up at the top of the StatDisk menu, you have something that says Data Sets. I'm going to click on it. Then it just asks you what edition of the book you have. We have the 11th edition. And And then they have all these different data sets you can go for. If I go down here, they have something called M&M candy weights. And there they all are. Red, orange, yellow, brown, blue, and green. Okay? Now, in the problem, it says, what do we want to do? Find the sample proportion of M&Ms that are green. Well, one trick was how many M&Ms are there they surveyed. By the way, these numbers here, do you know what these are? They're the weights of the M&Ms. See, there's other studies you can do. You could study the weights, and you might claim, hey, I think a certain color weighs more. Well, people have done this kind of stuff, okay? Anyways, there's 100 altogether. I did it this way. I looked at the row. Row 13, here's an 8 and an 8, so that's 16. I just added up the last number of each of the rows. Oh, look, there's a lot of blue. And that's kind of funny, actually. Because when I was growing up, there weren't any blue M&Ms. You know what they had that's not there anymore? They retired a color. Light brown. They called it tan. Yeah, they retired that one. And then they had America Vote a few years back, and they voted on blue. So now that's the most you'll find in a pack. Well, anyways, that's what they claim, right? It's not perfect. You don't get the same amount every time when you open a pack of M&Ms. But here's what they claim. They claim, Mars Candy Maker claims you're going to get 16% of their M&Ms are green. Well, how many did we get? 19%. We got 19 out of 100. So what if you want to do a confidence interval test on that, right? Well, it does all of it. Watch this. If I click on analysis up here, I can go down to confidence intervals. And if I say I want a confidence interval for the proportion of a sample, now it asks me just a few simple questions. What confidence level do you want? What do we want? 95%, right? What's our sample size? Well, 100, actually, we left out. What's the number of successes we had? We had 19 green? Okay. Let's evaluate. This is all under analysis. See, analysis has lots of things you could do. The third choice down was confidence intervals. Well, what does it say? There's my confidence interval. It says my proportion P is between 11% and 26.6%. What did the company claim? 16? Okay, is that in there? Did we catch it in the net? Yeah. And we have a 95% confidence that P should be in there. Scott, go ahead. Yes. Does your graphing calculator have something like this? No. Yes. What? To show you on Tuesday. All right, now, 0.99. What's going to happen if I make the confidence level 0.99? I want to be more confident. Well, in order to be more confident, yeah, it's going to be wider. So let me evaluate that. Now it goes from 8% to 29%. So if somebody said to you, hey, 50% of our M&Ms are green, you open up your sample and you only find 19 out of 100, you could use your little stats and say, listen, buddy, you don't have 50% green M&Ms. There's no way I would have gotten only 19. And here's the stats to prove it. See, that's the kind of tools we're empowering you with. You want me to go back to 95? Sure. That's the nice thing about technology is you can do all these calculations so fast. But now because you've gone through the writing, you're going to understand what they mean. That's the whole point of the stats class. Because, yeah, someone can tell you to what button to press, but that doesn't matter. It's the meaning. Now it means something to you, I hope. Here, I don't know if anyone noticed while we were at this, but I noticed something else under analysis I wanted to show you. See the next choice down after confidence intervals? Hypothesis testing. Cool. What do we want to test? Proportion, one sample. By the way, notice below it says 2 samples. We'll do that in Chapter 9. All right, let's go here. Oh, wait a minute. There's more choices. This is a little more complicated program. What do we want to test? It says population proportion equals claimed proportion. Notice the other choices. Less than or equal to, greater than or equal to, not equal to, greater than and less than. Okay? They go through all the whole gamut. Let's test if it's equal to the claimed proportion. What's our claimed proportion? The claimed proportion is 16%. That's right. Mars Candy says 16%. Now, we had a sample size of 100, and how many successes did we get? 19. Let's evaluate and see what computer tells me. Whoa, that was fast. Okay, they computed the z-value, the test statistic. Hey, notice what the critical z is? Plus or minus 1.96. It keeps coming back. There's the p-value. So the confidence interval, oh, they even gave me that, just in case you wanted it. Wow, this is a really nice program. Okay, now, it says fail to reject. Why does it say fail to reject? One reason is because the p-value is higher than 5%. What's another reason? The test statistic is not in the tails. Okay? So we're seeing all 3 methods at work here. This is a nice program. Here, let's suppose you open a bag of M&Ms and you got 50. Now, let's even say 40. What do you think the software would tell me? Let's try it. Evaluate. Reject the null hypothesis. If you got 40 green M&Ms, don't believe them that they tell you there's only 16%. Right? Why? Look how small the p-value was. 0. I mean, well, it's smaller than 0.0001. It was so small they can't even calculate it. You're not going to get 40 M&Ms that are green if only 16% of them are green. Wonder if I could get 20. 19 wasn't good enough. Let's evaluate that. 20 wasn't that bad. What about 25? See what you could do? You could do this stuff so fast when you have software. If you have 25, yeah, it's not 16%. You ought to reject that. Unless I change the significance level to 0.01. See, you could test this stuff so fast that it's just, well, no, you wouldn't reject. Okay, I'm going to put it away. Go back to this. If H naught has to be, well, mu equals whatever it equals, right? H1 can be lots of things. But the reason this is a two-tailed test is because H1 was what? Mu does not equal whatever it was. I forget. Okay? So it says that the p-value is twice the area to the right of negative 3.456. Here was the deal. We computed this. Okay? We computed that value. It was our test statistic. And so on the picture, and again, this is a t distribution. Well, we had over here, let me say, negative 3.456. So the p-value was twice the area to the right of that. Now that's a typo. Should be to the left of that, yeah. Right? It's going to be this area plus this area. I still am a firm believer that drawing these pictures can help you, okay, in terms of understanding how do I compute the p-value. Well, it's the area here and there. So this is 3.456. Right? So I think what I want to do is I want to go ahead and do an actual problem from the homework with you, rather than just an example. And I don't care which one we do. You guys tell me. Yeah, this is 8.5. I just want to go right into it. 17? You guys okay with doing 17? I'm hearing. You guys just went through it. Okay. Would you mind if we did 25 instead? You don't care? Okay. 25 a good example to do? Just majority rule kind of here. All right, I'll go ahead and do 25. Let me go back. Yeah, this is section 5, 8.5, and this is problem 25. Okay. Let's go ahead and I'll pause while we give people a chance to read. Remember, when you read one of these, don't read the whole paragraph. That'll take 5 minutes. Scan it and look for what they're asking. And usually in these problems, they're saying, test the claim that blah, blah. That's what I'm looking for. Test the claim. I don't even have the book open, and I can already tell you this is probably what it's going to say. Test the claim that. That's what I'm looking for. All right, I'm going to pause. Hooray, I found it. Test the claim that this sample. What sample? Well, I'll write it down in a minute. Is from a population with mu less than 1,000 hic. I've never heard of that in my life. The mean number of hiccups is 1,000 per minute, per hour. Hic. Head injury condition units. Oh, okay. How many have heard of those units before? Yeah, me neither. Oh, you have? Okay. Oh. Yeah, I believe it. And I don't want any slurs against rural. Never mind. All right. So I'm going to take the data that they give me and write it right in the list. I mean, I could write it on the screen, but... So I hit the stat button. And then it says, what do you want to do? And I want to edit a list. So I'm going to edit a list. Now, I was teaching stats in my last class, so I have a whole bunch of stuff in list 1. And you might remember how to clear it. If I go up on top of the list and press the clear button, it's gone. Well, if I press enter, it's gone, which I want to do. Or you could type over whatever you have in there. I mean, that's fine too. But anyways, we have a small sample of head injury condition units from a test of these child safety seats. So 774, 649. Uh-oh, that wasn't good. 1, 2, 10. Hey, 546. 431. And 612. Nice. So there's some data. What do you think? Do you think the population mean is less than 1,000? Well, that's what I want to test, right? So let's do this. Let's say, well, what would be the null hypothesis? Mu has to be equal to something. We're going to say that it equals 1,000 hiccups. Now H1 is mu is less than 1,000. What kind of tailed test are we going to have? A left-tailed test. I can see that because the arrow is pointing left in a sense, right? Okay. So let's see. I want to write down my test statistic next, right? I guess before I even do that, I need to know what my sample mean is. See, that's a good thing I punched this stuff in here, right? if I go to TI-83 plus, I have all this data in list 1, right? Let me hit second quit for a minute and just go back to my home screen. Yeah, second quit. Quit is right next to second, actually. It's just to the right of it. It's the mode button, basically. Okay, so I'm at my home screen, and now I'm thinking, I'd like to know what is the mean of that sample. And I could add it all up and divide, but it does it for me if you remember how to do it. I hit the StatMen button. This is kind of good. We're reviewing for the final this way. And where do I want to go? Calculate, choice number 2 there. I want to calculate some one-variable statistics. Enter. And then I guess I should tell it what list. Although if you don't, I think it'll do list 1 automatically. But I hit the second and the 1 to get list 1 up there. Enter. Oh yeah, I remember computing all this stuff back on exam 1. Remember that? So what's x bar? Looks like 703 and 2/3. All right, so we'll say x bar is 703.67. How about that? That's my sample mean. That's the best estimate I have of what the population mean is. But doesn't mean I can say anything yet, right? We learned in Chapter 6 that was a good, that's the estimator. Chapter 7 we would do a confidence interval. Now in Chapter 8 I'm actually doing hypothesis testing. I think we do. There it is. Yeah, Jeff pointed out that in order to compute the test statistic, well, okay, let me do this. Jeff, what's the formula that you're looking at when you say we also need sample standard deviation? Yeah. They call it mu x bar. Yep. There it is. Okay, and this is what you call your test statistic T, right? T equals x bar minus mu x bar divided by s over square root of n. You notice we need s. We need the standard deviation, which we learned about before. But again, the calculator gives me that. Boy, a long time ago I learned how to compute all this stuff, huh? Well, now I'm just going to use the calculator. The standard deviation is 272. Oh. That tells me something. Point what? 7.3. You know, I just want to go ahead and use the old rule of thumb we had. We said it's not unlikely that you're going to be within how many standard deviations? 2 standard deviations of the mean? Look at that sample mean at 700. That's a lot less than 1,000. But my standard deviation is 270. If I had 2 standard deviations, that's what? 540. That's way over 1,000. Yeah. Does anyone have a hunch what's going to happen when we perform the test? Do you think we're going to reject that mu is 1,000? Or do you think that we're going to fail to reject that mu is 1,000? You know, and this is all stuff that you can do without actually doing the computation. Now we'll see what happens. Yeah, so, okay, Jesse has a question. What is mu of x bar? I mean, that's my question too, right? We got to fill that in. Everything else I have. Well, do I know n? N is the number of, it's the size of the sample. And there's 6 values, yeah. Okay. So let's see, I need mu of x bar. So what I'm going to do is I'm going to put my 1,000 there. That's the thing I'm testing, in a sense. Okay? Yeah, because that's this. Basically what I'm doing is I'm saying, look, my sample mean is 703.67. I'm comparing that to 1,000 if you want. And I want to know, how does it compare? Notice if I'm very far away from 1,000, the t-value gets bigger. Well, more extreme. Smaller in this case, yeah. More extreme. Okay, and what do I want to divide by? Well, I guess I'm going to put parentheses here so that I remember that I'm going to need to take 272.23, 73, thank you, and divide by the square root of 6. Okay. So there's my big mess to compute. Calculate. I'm going to hit clear here because I want to have a blank screen when I mess around with this. So let's see, 703.67 minus 1,000 is negative 296.33. And then the denominator I have 272.73 divided by, and I'm going to put square root of 6 is what I'm dividing by. So my denominator is 111.34 basically. Of course, I rounded there, and I like to round as little as possible. So my way to do that is I'm going to take my negative 296.33. I'm going to divide by my answer, and I get that by hitting second and the negative sign. Okay, so there's my t-value, negative 2.66. You guys with me so far? Craig? Yeah, let me just do this. I know that alpha is 0.01, right? I know that I want to draw a picture of the t-distribution. This is the t-distribution. I know what kind of test are we dealing with here. Left tail. So over here, that's my critical region. 0.01. What I don't know, I guess, is my critical value. Right? We can't use inverse norm because it's not a normal distribution. We need inverse t, which your calculator doesn't have. So right, this is where that chart helps, okay? Remember I mentioned, yeah, the A3 chart. Remember, these are the Z ones. That's not going to help us here. We need the t distribution.
Are we going to have this on the test?
Yeah, you'll have that. That's on the card, I think.
5 degrees of freedom.
Why 5 degrees of freedom?
-1.
Okay, so we remember now that df, degrees of freedom, is n minus 1, which for us is 5. And we look on the chart. Should I be looking at the one tail or the two tails? One tail, right? Because this is a left tail. I can even see from my picture it's a one-tail test. Okay, one-tail test, and I want 0.01, so what column should I be looking at? Second column, right? Second column, let's go down degrees of freedom. We want 5. So the critical value is, yeah, I'm going to put a negative there, 3.365, right? And there's the critical value. Okay, last step. Well, because it's to the left. It's to the left. Whether it's negative or right, it doesn't matter too much. All you have to do now in the traditional method is this. There's no p-value to compute. Take t, put it on your picture. where would the test statistic go? Somewhere around here. T equals negative 2.66. So we fail to reject because we're not in the critical region. So the last step I'm going to do, which is people have been telling me, look, I'm having trouble saying the English. So how do I write down that I fail to reject? I would say this. There is not, oh, you guys are learning, sufficient evidence.
So the test you can't just write fail to reject.
Well, you can, but you won't get full credit. I said I'm going to put whatever's on that card. Is it on there? Someone said it's not. You guys better find it if it is. Okay. I mean, even if it's on there, if you can't find it, it's not going to help you. There is not sufficient evidence to support the claim that what? Yeah, that mu is less than 1,000 Hicks. How about that?
Is that okay?
I'm okay with that. That the mean last thing to say since it's noon. Why isn't there enough evidence? What do I mean there's not sufficient evidence? How big was my sample size? 6? Yeah, most of them were less than 1,000, but it wasn't enough. Do you see what this English means? What if I had 20 of them that were less than 1,000? Then you might have enough evidence. Do you understand what we're saying? I don't know. You have to test it each time.
So if you didn't fail to reject it,
If we rejected this claim, what would we have said? We would have said the population means less than 1,000.
and that's all we would have to say then?
Yeah, we'd say
We wouldn't have to write out everything like that?
well, you'd have to write a little more, but yeah, I mean that's basically what you'd say.